Hey everybody, welcome to lecture 11 at the start of week 6. And for today's mini lecture, we're going to be talking about groundwater. So before we get into exactly what groundwater is, I just want to quickly review the water cycle with all of you. So the water cycle includes anywhere that water is stored or transported between different spheres. So here we can have water stored in the ocean. We can have water stored on land in rivers and lakes. As fresh water, we can have it stored as snow and ice. We can have it stored as condensation in the atmosphere. And we can also have it stored beneath the ground as groundwater. Now there are different ways that water is transported between these. So evaporation transports water between oceans, lakes, and rivers into the atmosphere. We have condensation and precipitation. And when precipitation falls on land, it can either flow as surface runoff in rivers and streams, or it can infiltrate into the ground. So we're focusing on this infiltration process in groundwater today. So what exactly is groundwater? Well, groundwater is any water that is found below Earth's surface in cracks, spaces, and pores of soil, sand, and rocks. So that's the specific definition. And this diagram down here just shows you how that works. So below the ground, we can have an area that's unsaturated, which means that all of the pore space in the rock and sediment is filled with mainly air. Whereas below the water table or below a certain line, you have the saturated zone. And that's where you have a majority of the pore space in rocks and sediment filled with water specifically. So how does it get down there? I already mentioned this briefly. So infiltration is specifically the process of water sinking or percolating downwards into the ground. It increases when slope is low. So when you have flatter land, you get higher rates of infiltration. It also increases when the land is not highly vegetated. So the less vegetation you have there, the more infiltration that will occur. It will also increase when there's moderate or gentle rainfall. So very, very fast rains or very, very large rainfalls actually decrease infiltration because it can't saturate into the ground. So you'll get a lot of surface runoff when there's high precipitation events. And then finally, infiltration also increases when the soil is dry, so when the area is very, very dry. Now I've mentioned porosity, and we've briefly talked about this in previous lessons, but porosity literally just refers to the amount of pore space that's available in a rock or the amount of open space in a rock. And there are some different factors that control porosity in rocks. That includes the grain packing, which is how tightly together the grains in the rock are packed. Grain sorting, which is a sedimentary rock feature we discussed, so whether there's large grains and small grains or it's poorly sorted versus when it's well sorted. Typically, you get higher porosity when you have well sorted materials and lower porosity when you have poorly sorted materials. And then finally, grain rounding can actually have an influence on the porosity, so how round or angular the grains are. When the grains are very round, you get a higher porosity. Here's an example of different rocks and the types of porosities that they might have. So when you have very crystalline materials that are igneous, such as basalt or granite, granite specifically does not have very many fractures in it because it's very hard, so that's got a really low porosity. But basalt tends to have these vesicles and fractures in it, so you can have a pretty high porosity in basalt. When we're talking about our sedimentary rocks, which is what we see more often at the surface, conglomerates, which are sedimentary rocks with varying grain sizes, they have a porosity of about 20%. Sandstones that are highly cemented actually have a pretty low porosity because the cement fills in the pore spaces. Shale has a varying porosity, so you can have some porosity in shales, but we'll talk about how shales work in a moment. And then limestones are actually relatively porous because they get dissolved, so they can have a pretty high porosity too of about 30%. Now we also talked about this property called permeability, which again is how easily a fluid can flow through a given material. So that means that the pore spaces have to be connected in order for the water to flow. So you can have a high porosity but a low permeability if the pores aren't connected. So here we have an example of our crystalline igneous rock, which might be a granite. That has very small pore space and very low permeability because of it. Shales, or clay-rich layers, have many small pore spaces, but those pore spaces aren't connected. So that would also be low permeability but high porosity. Quartz sandstones are very well-rounded and sometimes can have high porosity, and because they're well connected can have high permeability. And that can be unconsolidated sands. And then glacial till is another example where you get low porosity and low permeability because you have those varying grain sizes. There are different zones in the groundwater, and I've mentioned this already. So there's the zone of aeration where it's unsaturated and the pore spaces are mainly filled with air. In the image on the right, that's at the top. And then there's the zone of saturation, which is where the pore spaces are filled with water. And then the water table, which you might have heard that term before, is just the surface or the line where those two zones connect. So the upper surface of the saturated zone. So what's important is how porosity and permeability actually influence the flow and the storage of groundwater. So when you have a very highly porous and a highly permeable layer, this is referred to often as an aquifer. It's a layer of sediment or rock that can transmit water economically, or in other words, we can, for a very low cost, bring that material to the surface to use. An aquitard is a low porosity and low permeability layer of rock or sediment that slows down the flow of water. So those are not good layers to get water from, but they're good layers to trap things or trap water. And then finally, an aquiclude is also low porosity and permeability, but it completely stops the flow of water, so you don't get any flow with aquicludes. There's also some differentiation between the types of aquifers that you might come across. So you can have an unconfined aquifer, which just means that it interacts with the surface. So it can interact or exchange water and be replenished from precipitation. Whereas there's confined aquifers, and confined aquifers are below an aquitard or an aquiclude. So they're not connected to the surface and they don't really get recharged. So when you're drawing water out from a confined aquifer, it's usually pretty deep below the ground, which puts a lot of pressure on that water. Hint, hint for something in the lecture. So again, just a note then of what actually makes a good aquifer. So obviously it would have to be high porosity or high permeability, but mostly unconsolidated materials or loose sediment make very good aquifers. So gravel, sands, and silty sands that are loose are great aquifers. But then consolidated materials can also be good aquifers as well. So any sort of fractured rock, and then also limestones with secondary solution openings. And then what would make a good aquitard, or, kind of slow the flow of that water? Obviously low porosity, low permeability rocks. Unconsolidated materials that would slow the flow of water would be loose sediment, including clay. So when you have really fine grained material. And then consolidated materials that slow the flow would be unfractured crystalline rock like granite, and then also mudstone or shale as well. All right, so that is the end of today's lesson or mini lecture. Go ahead and continue on to finish today's lesson on the Dismal River.